Hello and welcome. My name is Mark Mancuso, and this is a version of a presentation I was going to give to NCECA in 2020. Color is all about movement, and I'm interested in showing you ways to make color blending a little bit easier. We're going to move the math around and move the processes around to where it's more intuitive and hopefully faster and even safer. So these are the slides that I will present one day. So, color is all about movement, as I said, and the idea of liquid volumes as wedges means that we have a way to look at the process from the math side and make it a little bit simpler, and the process from the mixing side and make it a little bit faster. See, we get all caught up in the tools of mixing when all we want is something a little bit faster. And I think of this more as scouting. We want to do our color blending in ceramics as scouting rather than all the math to begin with just to come up with them. So in ceramics, we have a bunch of different materials that we're likely to blend. Liquids, clay slips, clay bodies, recipes with numbers in them and things like that. And this talk is going to be about the fastest moving of them, the liquids. And so we have underglazes and glazes and things like that. And we're going to start there. The problem with liquids is that they're a little bit sassy. You look into a jar, you buy a jar of underglaze, and what do you have? You don't have color. You have a jar full of sass. You want to know what color it's going to be? It says, who wants to know? You would say, how much do I blend? How much do I use? It says, I'm not telling you. And you say, well, how long is it going to take? And the kiln in the corner starts laughing because it's all a big mixing scam. We don't have any way around that. So my methods are going to be to make it a little bit faster and a little bit easier. Let's see about how. My approach is to see the contents of the jars not as colors, but as liquids. Liquid wants to help, but doesn't know how. For huge amounts of liquid, all kinds of major things can happen. But when liquid's inclination to move is coupled with our ability to build containers, liquids can do math at much smaller and sensitive scales. Here are some of the shapes we might capture liquid into. Now in other videos, we'll talk about how to build actual contraptions that turn liquids into these shapes. For today, though, just think about the shape of the liquid itself. All of these are pretty regular and have predictable sides and tops. Note that some liquid surfaces are parallel to each other, while other surfaces spread apart. This movement of shape maps quite well to the way we'd like our number sequences to change. To make use of it, we can build contraptions that measure out lots of equal proportions of liquids, or lots of portions of liquids that vary slightly, based on whether or not they have any angles and how angly they are. This talk will focus on using only two of these shapes, the triangle and the rectangle. To the right, you see a double pointy wedge thing. This is very important. I should have made that particular one the biggest. Oh well. Two triangles have been fattened up into wedges and have been arranged in an X pattern. And that's it. The wedge X concept is the secret to this whole thing. The rest of the talk unpacks how this is so. Let's start looking at our materials. A liquid can do math, but the poor thing gets distracted. Let's give it some direction. The syringe is often an actual tool we use to make portions. But as a metaphor, it refers to the shift in approach that inspired my techniques here. Liquid has big questions about its past, its present, and its future. How we answer those questions for liquids represents the containers and processes and outputs that I'm talking about. I mentioned a bridge earlier about materials on one side and processes on the other side. This bird's eye view of the process shows how drawing and planning and calculating participate in the different tasks that we normally take for granted. But don't memorize this today, that would hurt. It's taken me several years to pull things apart and put them back together in this way. This talk is focusing on a kind of middle space between drawings that I see as decisions about numbers and the 3D space where we have to wrestle with materials and gestures. This middle space is a kind of 2.5D space where my ideas might save you some time. But first, I have to move some of your favorite ideas out of the way. The most radical change here is what we do with all of our quantitative urges that have been so lovingly, if sadistically, hammered into our brains. The calculations are going to happen last, if at all. You only need to make note of one or two basic facts. You might make note of how much you're going to use up in the tests, or how big is your sample going to be, or some maximum amount of colorant you're using. After the process is done, you refer to those minimal notes and derive what the actual proportions of any samples are that you happen to like. When you do it in this way, if all your blends turn out to be duds, you can just throw them away. You didn't need to kill an afternoon just to get them in the first place. Which leads me to the next radical change. With no need to use quantities to begin with, unless you're refining previous recipes, you can also ignore the spoons and the cups and the scales. They're the main time sink of the process and a major downer when what you really want is more color choices. Isn't that the point of all our efforts, to get a range of colors so that we can choose among them? I mean, my own work has a lot of fun with having color choices. I did those tiles the old-fashioned way, but after a while, even I wish for some other way to spend my weekend. I had planned here to have a photo of the biggest box of crayons I could find, just to remind you how much fun it is to get one, but I forgot. I'm inspired by all the digital tools available and hope to bring to ceramics some of the language and methodology of graphic design. In ceramics, we might well crave colorways and blending of color families. If as a painter you were inspired by the luscious colors of these vegetables and produce, you know what work is ahead of you. But a ceramics person might well give up before they even start. I'm going to show you that building color gradients with ceramics liquids can be as fast and as intuitive as this nifty graphical interface I saw on the internet. You pick two colors, just like we might pick two jars, and then wonder, what blends can I get out of them? This graphical interface lets you choose how many blends you'd like to see, and the computer just spits it out instantly. Getting 15 blends is as easy a process as getting 5. Nowadays, we don't even think of it in the digital world. So in that run-through, starting with those lovely rice field terraces where water is doing work for us, I'm rethinking how liquids work in ceramics so I can train them to participate in blends that would be too time-consuming to perform the old way. And that's going to require a review and a restructuring of the tools we're already familiar with. You know what that means, don't you? We're going to have to revisit our old friend, the two-way proportional line blend. Let's look at the main tool we've used, the line blend, and break it down and see what math is underneath. The triangles that I'm showing you in the little drawing is a representation of the way the numbers change in the line blends that we tend to do. We have a maximum value and a minimum value, which can be literal. Or like the middle set of triangles, we can sort of do it intuitively. And the third set of shapes is a rectangle and a triangle and a triangle over it, which basically means we have a set number of portions that are all the same that we're mixing something into. And so these three images represent most of what we try to do in the process. And the middle one, as intuitive as it is, it still makes you go with the gram scale and the spoons and stuff to deal with it. Maybe there's another way. So the fast wedge concept has to do with the idea that all of our drawings and numbers could be represented by a triangle. And the bridge I talked about is that that representation on the paper can be fattened up to something like 2.5 dimensions and become useful. On the liquid side, we're going to move it down a dimension from 3 dimensions to sort of 2.5 dimensions. And so this image shows you the crux of the whole thing, where if you take liquid and you make it flatter, like those little blue drawings, we're going to have a way to manipulate them and drain them. And that our math from the two-way blend has several things about it. And that's those other little triangles in the image. The angle, which represents the range of values that you're trying to do. The slice, which is basically how many portions do you want to get out of this. And then the notion of the last triangle, where you have the T of fast, which is take or trap. And so you're going to be doing all these things, but you still have to get it out of the system in order to do it. So let's see about the key manipulation of liquid. The only problem I can see with liquids is that they're not only sassy, they're a little bit impatient. If we can control a leak when it starts and stops, and where it ends up going, then the leak is no longer a problem. The leak is a portion. And so what we're going to do is we're going to look at simple containers about how to control leaks and where they start and where they stop, because the liquid, when it drains, will help us out and do the math. And that's what this slide shows you. A simple rectangle of liquid imagined as being in a container with a vertical set of holes. Well, those little red squares are bits of tape, let's say. And this is the way we turn on and off the little drain. And so you might imagine that if they were all closed, you have all the liquid and a couple different variations. Let's see what those variations would look like. It might help if you think in terms of a stoplight. Basically, where something is waiting is yellow, just like our slow down color. When something is taped up, it's stopped, and when you remove the tape, it's like the green of a stoplight. And so here we have 4 versions of our liquid columns and different ways of leaving tape and opening tape. And if you spend some time with this idea, you see that you get a whole bunch of different portions depending on the shape of the container and how those tapes are spaced out. And so you might well say, well, you know, I have a certain shaped container. What if I want a different number of slices? And then we come to our other drawing, where you can see that at the bottom you see the notion that we can trap or take different ones depending on which ones we would like. So we'll see a little bit of flexibility there. So let's look a little bit more detail at the notion behind the way the math happens. Intuitively, we look at these stairs and we see an angle. The handrail is really smooth, and the steps are very specific. And this is really analogous to our intuitive method of just wanting to blend colors, and also our numerical, quantified method of having some math ahead of time, or some decision going in ahead of time, to where you can use the steps, or where you can just imagine that you're going up or down and coming up with a color variation. When you think about doing this with 2 colors and flipping them head to toe, you get the notion of this X. And so this is why sometimes the wedge is going to have 2 different angles to it. If you remember from the earlier drawing, we saw that there was a rectangle that was equal portions of things with a triangle above it. This is where you might have, 100 grams of slip in a whole bunch of portions, and then you're mixing different amounts of color in it. And the double wedge version here is where you would have 9 parts of your one pure color down to 1 part of that color and flipping it to where the 9 parts of one lines up to the 1 part of the other, and you get a very balanced X. But you might also ask, well, what if you don't know how many slices you want? How do you come up with a division that makes sense? And so in this drawing, I'm showing you a graphical way to take just parallel lines, any kind of parallel lines, and arranging your conceptual liquid volume over it. And as you can see, you could line it up with 7 slices, you could line it up with 12 slices, or you could be all crazy and line it up to 17 slices. It just doesn't matter when it's a position. But you certainly wouldn't do it if you had to do it with a calculator. And so when you transpose a simple geometry from the 2D drawing onto a 3-dimensional volume and have that be, say, drains in our little cup, then that's going to work out for us. Here's a simplified version of equal portions when you don't really care how much material you start off with. That one cylinder holds liquid, and as it happens, I fit in 39 straws, and they're all jammed in there. Well, the liquid says, yes, I'll do this, and it balances itself out. Then the liquid is waiting, and you push all the straws down to the bottom of the container where there's some kind of plug there. I'll talk about that in another video where we talk about literal contraptions, how it works. So this liquid isn't being drained, it's being trapped by the straws. And so no matter how much water you start off with, it's now divided into 39 chunks. Well, it could be 39 because it's this container and these straws, but it could be any other container and any other number of straws. So this slicing method of the straws and the taking and the trapping method of pulling it out of there is going to work for any container in any kind of regular straw-like material that you may happen to have. And so one of the important questions in the number sequence is, well, what if the numbers are too close together? What if your color is not that subtle and you need a bigger range of changes? Well, you line up all your straws, let's say, and your take is only some of them. You don't have to pick neighboring straws. You can always skip them. And so the idea of this library picture where you have those movable shelves will help you remember that even though you set up a certain number of slides or a certain number of drains, that you don't have to pick each one, that the math has happened for you at the highest resolution you could possibly want, and then you don't have to take them all. And when you don't take them all, you get a coarser resolution, which may suit your project better. And here is a picture of one of the earlier prototypes where the straws aren't in a whole bundle, but instead they're all in a row. And the angle of the liquid that we've been talking about is not because the container was angled, but because the liquid became angled before you jammed all the straws down. And so this will give you an idea of different kinds of contraptions where the even-numbered straws made equal portions, but they became proportional and looked like a triangle and looked like our wedge simply because you turn the container at some kind of angle. This is very fast, and I hope it'll now make things a little more intuitive for you. Well, all of that can get a little bit theoretical, and in all honesty, the next section of this, which will happen on another day, is going to be about building the contraptions that follow along with the theory. But I want to leave you with a couple slides about making this theory work for you in terms of a little mixing tray. So what you see in the first slide is that I've taken a slab of clay and made grooves with a paper clip. And so that number of grooves happened to fit into the tray. I didn't know how many there were going to be. And so you make a groove down an angle. And so if you remember from the drawings, the two different kind of X wedge shape, when they're over each other, it's a rectangle divided from corner to corner. And so then you put an index card, jam that right down in there. And now what do you have? you have a balanced set of little troughs. So you take one color and you pour it into all the troughs on one side, and you take your other color and you pour it into the troughs from the other side. You see where this is going, right? And then you put all that aside and pull up the card. So the little card groove is not enough for them to leak out. You mix those up, right? So each of those rows is exactly set up itself, and then you paint it on a little tile and you run it through the kiln and you see whether you like it. If you did like it, if you do come up with something, then it shouldn't be too hard to figure out, well, how many grams was it in the biggest one, and how many grams was in the smallest one. You could leave yourself a trail of breadcrumbs. You could go back and you can find out. But the nice part of this method is that it would probably only take you about 20 minutes or so. You get a really nice color blend, even if you didn't want to know any of them. And after you get it out of the kiln, you say, I like this one and I like that one. And then you know you have an idea of whether to get it. But if they're all boring and you don't like any of them, you haven't lost as much time. So that's the whole idea of the process. And watch it several times. I'm going to be doing more work about building different contraptions out of things that you have around the studio. Think of trays and all commercial objects that are like cups that stack, plastics that you can drill through, straws of many different kinds. And I have a feeling that if you get this idea into your head, you may not have to go all the way toward the weight-driven methods, and that these volumetric progressive changes among liquids might well save you some time. So thank you so much for your attention. I hope to hear that it works out for you. Goodbye.